welcome to another session of Introduction to Astrophysical Fluids. In this lecture session, we will discuss a new topic, which is the turbulence. Okay. Previously, we have discussed several properties of neutral fluids, plasma, and in plasma, we have discussed different properties, the definitions of different types of plasma, how to describe a plasma, how from kinetic theory, very briefly of course, we discussed how from kinetic theory we can we can have a transition to fluid theory or continuum. Then we have seen that there are multi-fluid pictures as well as the monofluid pictures, and this depends on which length scale and which time scale I am interested in. Okay. Now, after that, we have also discussed, so the monofluid model, as you know, is the magnetohydrodynamics, okay, and then we, of course, discussed the various properties of magnetohydrodynamics, and then we have discussed a little bit about their application or importance in the framework of space and astrophysics, okay. Now, in this lecture, it will be a different topic, so turbulence. So mostly I will discuss in this session and also in the next lecture the general properties of turbulence, okay, for normal incompressible fluids, and only I will just discuss very briefly about the turbulence in plasmas and also their importance in finally for astrophysical context, or I mean space physics context. For example, in the turbulence in solar wind is a very hot topic of research, for example, okay. So as you can easily understand here that previously when we you can recall that when we discussed the stability and the instabilities of the fluid, okay, then we said that we start from some arbitrary steady state, and then depending on whether the steady state is stable or unstable, okay, it responds to an external weak perturbation either in terms of wave modes, okay. So if the steady state is stable in nature, then it responds in terms of the linear wave mode, so that the system tries to get back its original configuration. Or if the original steady state is unstable, then basically the small perturbation which is applied actually grows in time, and after a certain extent it is no longer a small perturbation, and we cannot any longer analyze this using linear techniques, and then we are talking about general instability. Okay, the onset is of course the linear instability, that means this system is treated under linearization, okay, but of course when the perturbations are growing larger, then we have to take either nonlinear techniques into account, or we just have to say that okay, we cannot do analytical treatment, and then we can do some numerical treatment for those type of problems, okay. Now, it is true that in such cases, since the perturbation becomes very large or important, then actually the fluid motion becomes practically unpredictable, okay, or unpredictable, okay. Now, what is the meaning of that? That means, let's say you have two infinitesimally closed fluid particles, and now with time they are now diverge hugely, okay, both in space and time, okay. So that is something very important. That means if you want to track some particles, so let's say if you have a flow field like this, and if you track that, okay, let's say these two particles were very near here, so now these two particles, for example, we want to track them in time, and basically maybe after some time it is here and it is here, okay, we don't know. So the irregularity is observed in both space and time. So such a flow regime where the system is undergoing, or the flow is undergoing some very non-equilibrium state of motion with irregularities in both space and time, we sometimes say disordered motion in space and time is called turbulence. Okay, and of course you can easily understand that if for example, if we as just I described 1 second ago, that if you have a flow field like that, and the velocity at this point is v, and then the velocity at this point, I mean, tracking is not very easy, because I mean it does not say. So for example, just by knowing, since the fluid is really totally moving erratically, just by knowing the velocity at this point and this point, you cannot really, or this point, you cannot really predict the nature of the flow in some subsequent instant. Okay, because after some point, after a small while, okay, after a small time interval, this particle, let's say here, this particle, let's say, sorry, this particle, let's say here, this particle, let's say here, this particle, let's say here. So 3 particles are totally in different places. So you cannot, when I am talking about particle, I am just simply talking about fluid particles in Lagrangian sense. So in practical sense, you cannot picturize the fluid motion. Okay, for example, if you have a flow, very laminar type of flow, then you know that layers are like this. So just knowing this type of the profile, the velocity profile here, you can have a strong idea or clear idea of the velocity profile here, right? But here in turbulence, this is not possible. So that's why it is not very much practically important to know the 1-point variables at any point of time. Of course, you can know that as an information, but to know the global picture, whether globally the system gives some vortex like structure, or the system is moving in forming some type of 2-dimensional sheet type of thing, well, this type of thing is impossible to extract from such type of information. Okay, and that is why it is basically much more important. So what happens that the total system is a chaotic motion. Of course, the formal chaos is a different thing, but just roughly speaking, the turbulence motion is nothing but a chaotic motion, a totally disordered motion. So we need the statistical study. So what we can do, instead of just determining the velocity, okay, or the pressure at one point to another point, what we can do, we can take the average of this such type of points. And if you do a large type of large number of, if you prepare an ensemble with large number of members, that means you prepare a large number of imaginary systems, okay, with identical fluid particles, okay, with identical flow field, and we just have difference in their initial conditions, okay, and then you just specify one time point and one space point, and you take that point in space and time from each member of the ensemble, and you do the ensemble average. If you can do that, then this average can have some meaning. Okay, why? Because anything which is randomly moving, we know that in statistics this is much more easier to capture the behavior, because we know that its distribution actually should follow something very well-known thing, either Gaussian or well, it is a perfectly random thing, then it should be a Gaussian type of distribution, or it can be something modified Gaussian or something nearly more complicated like that, but at least we have some behavior of the distribution. Okay, that's what I am trying to say. That's exactly the same type of picture what we have when we are talking about kinetic theory, for example, right? We have a large number of gas molecules which are moving here and there, and so we are not interested. That's the same philosophy, that we are not interested in the behavior of a single particle at one point, because this is a total mess. Then our interest is to know that in phase space for a given x and p, how many particles should be there. Okay, so just analogical to that philosophy, here we are simply saying that here we are not interested in the just because once again the movement, the fluid particle movement is totally a mess. Okay, it's totally unpredictable, and that's why we are not interested in the individual values of the velocity, pressure like this at every space and time, but we are more interested in the average values and to know that if they can do, they can give us some meaningful information. Okay, so since perturbations are the source of turbulence, then we can actually think of decomposing every fluid field as a mean field plus the perturbation part or the fluctuating part, and sometimes we call this as the turbulent velocity or turbulent field simply. I mean, turbulent field is the general thing for the fluctuation part. So this type of decomposition so this type of decomposition was done by Reynolds, and that's why this is known as Reynolds decomposition. Okay, so what you have to do, that you have to decompose them into two parts. One is the mean velocity, that is the ensemble average once again, and this is the fluctuation. That means simply this means the instantaneous value of velocity at every point and space and time, okay, minus the ensemble average value. Okay, so we just call this ensemble average value as the mean velocity. Now it is true that here we are taking ensemble average, that is true, but I mean, well, theoretically it is much more proper to talk in terms of ensemble average, but I mean practically it is much more easier to take space average or time average, because although we say that ensemble is making, so ensemble can be made in numerical simulations, but in practice you have only one system, right? So you cannot, so for example, if I tell you to study, for example, the behavior of turbulence in a river, for example, then you need to create 1,000 rivers at the same time, and this is not possible, right? Same time, and so I mean identical. So this is just something which we talk in the for the sake of theoretical how to say, like theoretical correctness. But in general, what we do, that we assume that our system is either homogeneous enough so that the ensemble average can be replaced by spatial averages or space averages, or our system is stationary so that the ensemble averages can be replaced by time averages. Now if our system is ergodic, okay, now what ergodic is, it's a tricky definition, but at least here just you have to simply know that this is a rough definition, that if the system follows, if the phase space density, okay, of the ensemble points, okay, follow the Liouville's theorem or something like Liouville's theorem, okay, let me just not going into this Pandora's box, okay, so then we can say that the system is ergodic and all these three averages are practically equivalent. So although we are talking in terms of ensemble average, you remember that for a practical purpose, for example, even if you do a numerical simulation, what would you do to take averages? Would you really take, again, start every time, run the simulation 1,000 times? You don't do that. If you take 1,000 snapshots and take the time average, or you take just for a box at a time instant, and you take all the points in the box and you take the space average. That's practically what you do. Okay, so the basic, and most of the time it works. It works means it gives us something which we can expect from our intuition or from the first principle or from heuristic logics. Okay, now that simply says that the turbulent systems, although they are very disordered, randomly moving, ergodicity can be very well applicable for those systems. Okay, now here you can see that, so these are all about these three types of averages, and once again for a robotic system these three averages are equivalent. So for our case, what we will do is simply Reynolds decompose, and we will, according to our convenience, from time to time we will take space average or time average, okay, which will replace the ensemble average. So then the fluctuation part. Now the fluctuation part actually by definition is of mean zero, and that's the definition of fluctuation. If you take the fluctuation in both sides, so that the average in both sides, so the average of the average is nothing but itself, so this will be then V average, so V average will go away, so the V average of this V tilde is simply equal to 0. Okay, so you see that the average of this is 0. So the 1 point statistics is also not much useful for the velocity, because this is simply 0. Okay, now not in this lecture, but in the later after 1 or 2 lectures we will discuss that we will properly address this Reynolds decomposition method, and thereby introducing some important things of turbulence. Okay, but here just for your information I would like to mention that just by doing Reynolds decomposition, the take home message is that 1 point statistics for this tilde is not just interesting. Okay, either you have to do well. Now you can say, okay, we can, at least the first order statistics. Now you can of course do V square. Okay, and that can give you something. Okay, now at this point of course this is possible. Okay, so 1 point statistics of first order is not possible, so there is another possibility. So maybe higher order moments can be interesting. Okay, and actually you will see they are, but there is a seminal paper. The total thoughts about this turbulence was changed after Taylor, who suggested in a seminal paper in 1935 that actually for studying the turbulence in incompressible fluid, instead of 1 point velocity functions, one needs to study 2 point velocity correlation function. Okay, so that means the fluctuating velocity at 1 point, if the time for a given time at 1 point in space contracted with another point in space. Okay, and its evolution. So that is the correct thing to study. Okay, how actually Taylor thought that, I will come later into that. Okay, so these type of quantity has to satisfy 2 properties. One is that it should go to 0 when r is very, very large. That means 2 very, very distant points. So it's really impossible to be correlated. Okay, and another thing is when r is 0, then this is simply the exactly what I just said, that the higher order moment for V tilde. So since this also comes as a special case for this correlation function, then we are just not going into this one. So we simply say that, okay, we just follow Taylor, and we will be interested into the study of 2 point correlation functions, and the 1 point quantity will be simply coming as a special case of this. Okay, when your r is 0, that's okay. And actually then we use this quantity in order to normalize the velocity correlation function, and which is the traditional Pearsonian correlation coefficient. People who are used to statistical methods, you should know this Pearsonian correlation coefficient. So this is simply that this is denoted by this sign sigma, sigma of V tilde, which is equal to the ensemble average of V tilde at x to contracted with the V tilde at x plus r divided by the V tilde at x square averaged. And if you do that correctly, you will see that sigma V, actually one can show that, always should be within -1 to +1. Okay. Now, at this point, so up to this point, we have not said any assumption on like the nature of the turbulence, that means statistical homogeneity or isotropy, anything, stationarity, nothing. But at this point, for the sake of analytical simplicity, we have to introduce two assumptions of turbulence. One is statistical homogeneity, another is statistical isotropy. And what is the advantage of that? If the system is statistically homogeneous, so statistically homogeneous does not say the system is absolutely homogeneous. When a system is absolute homogeneous, some property is totally uniform in space, that is the homogeneous. For example, if you are taking an incompressible fluid, okay, it has a density homogeneity in space. That means at every point the density is constant. Okay. Now when we are talking about statistical homogeneity, it does not say that it has a, at every point some quantity, for example the velocity is uniform. What it simply says that the 2-point correlation functions of, so this is another way of writing sometimes, so either you can write this or you can simply write this contrast sign. Yeah, so the correlation coefficient, either normalized or not normalized, that is not a big problem, but this coefficient, correlation coefficient, this part, okay, should only be a function of the distance between these 2 points and not really depends on where the origin is. Okay, of course, to be very honest, there should be a t, which I forgot to give, so I can just add that. I add in a different color so that you can remember. Okay, of course this is possible, so this is yeah, there is a t dependence of course, but just for the space part, this is not depending on the origin. This is not depending on the x, but only, so this is, the absolute position of the points doesn't matter, so only the mutual distance between 2 points that matters. And so now what happens, that you can actually find in your system all the points which are, let's say, arc distance apart, and for this type of couple of points you can calculate this quantity and then you can just take the average, and that will give you a reasonable estimate for this correlation coefficient, and you will see that this will only be a function of r and t. Okay, and if this is statistically isotropic, that simply says that in addition to this one will simply be a function of not a vector r but only the modulus of r. It's even much more simplified situation, so it has so-called spherical symmetry and of course the t dependence. Okay. Now in the year 1938, so von Karman and Howard, these two persons, they after doing some maths, they actually showed, okay, some tensorial arguments. They showed that the most general expression for 2-point correlation functions, which they now call like this because this is a tensor, right? So in general this is a tensor. So here, although I have written here this dot product, you can actually take, so von Karman and Howard actually took that as a tensor product. That means in the normal form you have to have this type of thing. Of course, in several literatures sometimes you can have this, so this is nothing but the trace of that tensor if you do that. So to be very honest, this should be like this. Okay, that should be the tensor product. And in year 1938, they said that the most general form of this tensor is, which is exactly equal to this, will be equal to some function of r only, that means the modulus of r vector, some function a times ri rj. So once again, what is this? You can easily understand this is nothing but r tensorial r plus b, which is another function of modulus of r times Kronecker delta ij. Okay, so using this formula, okay, it was much more simpler for them to find, according to the Taylor's suggestion, del t of Rij, that means the evolution of the correlation function, and then they did it. I will be coming to that point later, but first let me just tell you that although, from the very beginning of this lecture, I just presented you the analytical pathway for turbulence, that means how starting from one point quantities, people switch to 2-point correlation functions, and finally they tried to make study their evolution, okay, for statistical homogeneous and isotropic turbulence. But historically, okay, we actually did not do like that. Historically, people actually attacked the very problem of turbulence in a slightly different way. Okay, so analytical treatment was there, of course, but even before that, in the year 1921, Richardson, who was an expert of weather forecasting, okay, so he basically gave a very schematic picture of the phenomenological energy transfers in different scales of turbulence. So at this point, I have to mention that the notion that a turbulent system should behave like a multi-scale system was already conceived by that time, although by mathematics it was not properly shown or it was not properly exploited, this multi-scale properties, but people have in their mind that in a turbulent system the total flow should have a multi-scale nature. That means the system has actually different forms in different scales. Okay, so and according to the scale, the system behaves actually differently. Okay, if irrespective of the scale the system behaves identically, then there is no problem. Okay, but what I am saying that when a system, for example, if it is a laminar flow, then if you just cut the laminar flow lines in small, so you have the layers, now you cut the layers transversely to its flow into smaller and smaller parts. Well, the laminar nature will remain laminar, right? Now in a turbulent flow, that is not the correct thing. So if you just want to go to smaller and smaller scales, the picture can be different. Okay, and that's, I am coming to that, and very, very crude and phenomenological view was conceived by Richardson already in the year 1921, which was much more earlier than von Karman and Howard and even the work of Taylor. So you see, and to understand these things, we have to just have a look at the governing equation of the fluid flow. So we have told many things about velocity, 2-point velocity correlation, but till now we have not talked about the equation which is governing the velocity and everything. So that is Navier-Stokes equation just for a normal incompressible fluid. And this is nothing but del V del T plus V dot nabla V is equal to minus gradient of P plus the viscous term nu times Laplacian V plus a forcing term. There should be a vector sign over the forcing term. Yeah. Okay. So this is the external forcing term. So we, we have to do something now starting from, so we have to first understand that whether starting from Navier-Stokes equation, we can even roughly try to understand the turbulent regime. Okay, because you know that the same equation actually can guide, can lead to laminar flow as well as turbulent flow, right? So actually what happens that, as we have already seen in previous discussions, that when the perturbation grows, now if you remember that the nonlinear term can no longer be neglected. So if you remember that when the perturbation is weak, we can linearize the system just by neglecting the second order smallness, I mean the terms with second order smallness. Okay, for example, the term like this. But when your perturbation is not negligibly small, then I mean is not of first order, basically it's larger than that, then the nonlinear term cannot be neglected anymore. Okay, and then simply we are beyond the regime of linear instability. Okay, and it actually simply leads to, this is one of the way, of course. So basically how to reach to turbulence, this is another fundamental and very deep question. So to be very honest, turbulence is a very deep and complicated subject, and actually more than one course can be given on turbulence. So just in one or two lectures it is almost impossible to present turbulence. So then I mean in this way, when we are beyond the regime of linear instability, we reach, or rather attain, the regime of turbulence, and which is simply described by a clear dominance of the nonlinear terms. Okay. So because when the perturbation now grows larger and larger, then the nonlinear term, basically they are being the nonlinear in perturbation, they will grow much faster than the other linear terms. Okay, that's I mean very common sense. So in Navier-Stokes equation, there actually exists a dimensionless number Re, which represents the importance of the nonlinear terms over the viscous terms, and that Re is nothing but VL by nu for an arbitrary length and velocity scale and the coefficient of viscosity, and this is known as the scale specific Reynolds number. And if the system's Reynolds number corresponding to the largest scale and the largest velocity is very greater than 1, then we say that the system has achieved turbulence macroscopically. Okay, macroscopically means, so what I am saying, that in a system, such a system, the largest scale is the scale of this box, for example. So if we have a box where there is a turbulent fluid, so the box size is the largest scale, or rather roughly largest scale is the scale, roughly the order which we can see in naked eye. Okay, so this is the macroscopic scale, and we see that in the macroscopic scale, if there are this type of chaotic type of, I mean arbitrary motion, then the large scale is this one roughly, or this one. Of course they are of the same order roughly. Okay, so if that Reynolds number is very greater than 1, then the system is turbulent, the flow is turbulent. That is by definition. Okay, now at this point, when we have already defined Reynolds number and the regime of turbulence depending on that, it is very important to remember that when a laminar flow switches to turbulent motion, initially the symmetries of the Navier-Stokes equation, that means the homogeneity, that I mean the Navier-Stokes equation is actually very much symmetric. So in laminar, if you are thinking of normal the equation itself, so it is actually invariant under the origin, I mean in both space and time. So whether you let the fluid flow here or in London, that doesn't matter, or today or tomorrow, doesn't matter. I mean if the other conditions, for example the temperature, pressure, they are kept constant, then there is no explicit depending on the space and time origin. And also Navier-Stokes equation is Galilean invariant. Navier-Stokes equation is also I mean invariant under symmetric under time reversal. So all these things are there. Okay, okay, there is a small catch. Okay, if no, okay, so Navier-Stokes equation is invariant under time reversal only when the viscous term is not there. Okay, otherwise there can be time, the viscous term can actually destroy. So to be very formal, the Euler equation is symmetric under time reversal, but viscous term, which dissipates energy, actually kills the time reversal symmetry. Okay, but all this symmetry which it has, for example, homogeneity in space and time, okay, isotropy, for example, okay, so this type of symmetries are gradually lost when the flow is getting more and more turbulent. That means its Reynolds number increases from 10 to 100 like this. But when the flow is completely turbulent, that means the Reynolds number is greater or equal to 10 to the power 4 or large, even greater actually. Then the good news is all the basic symmetries of the Navier-Stokes equations are expected to be restored statistically. Why this is so, this is not really very much clear, but this is actually very, this is a crude approximation, and somehow people have applied this hypothesis and they have seen that this works. So to be very honest, this is something which already happens in nature. That's why we expect for any general system in turbulence that when the turbulence is completely developed or fully developed, okay, then all the Navier-Stokes symmetries are restored, but in statistical sense, and that's why it somehow justifies of our previous hypothesis of previous assumptions of statistical homogeneity and isotropy. Okay, so actually homogeneity in both space and time, to be very honest. And now we have discussed the analytical approach of turbulence in terms of 2-point velocity correlation or 2-point increments. But as I just said, that historically the phenomenological view of turbulence came much earlier using Richardson's cascade and Kolmogorov's equilibrium hypothesis. Okay, and that was done actually in not in direct space but in Fourier space. Okay, for that one this part I will be discussing in the next lecture. So from this lecture, the message is that turbulence is a disordered out of equilibrium motion in both space and time, and the non-linearity is dominating. So and also 1-point quantities are of not importance, although statistical description is important. Then Taylor said that the 2-point correlation functions are the quantities which we have to look at, and then von Karman and Howard, they analyzed that and studied their evolution, and finally we said that okay, so all these things are there, but just by of course how to really, without knowing anything, how to characterize a turbulent regime, and for that we started looking at the governing equations. Of course, von Karman and Howard, when they derived their del T of Rij, they also used Navier-Stokes equation. What else they could have used? Okay, so now just by introducing Navier-Stokes equation, we said that there is a dimensionless quantity called Reynolds number, a large value of whose can correspond to the domain of flow regime, which is completely dominated by non-linearity and which is the turbulent regime. Okay, in the next lecture I will come into the Richardson cascade picture and the Kolmogorov phenomenology. Okay, thank you very much.